Okay, so we're going to continue our discussion on non-Newtonian fluids. I hope the quiz, you're awake now, you're ready. The brains are working, so we can actually add some new knowledge. So just a quick review. So last time we have derived velocity distribution for Bingham plastic. And just a quick recap. So the way we model Bingham plastic is the fluid that is typically a combination of a fluid and a solid, and sometimes kind of behaves either way because of that. So I need a certain stress, threshold stress that we call yield stress for a fluid to actually start behaving as a fluid or a Newtonian fluid. So up until I reach that yield stress, nothing really happens. The fluid doesn't move. Just like the solid doesn't necessarily move when I actually stress it or apply shear stress to it. So the way we model that is that, for instance, in the case of tau yx, we say, this is minus mu dvx dy plus tau 0, and mu 0 is what my traditional viscosity coefficient was, and tau 0 is this yield stress. And that's my relationship between shear stress and velocity distribution in case I actually have shear stress that is large enough. In case that it's not, so it's a bit of a circular business, okay? I have two relationships, or I have non-existing relationship between shear stress and tau, shear stress and velocity gradients in case that this shear stress is not high enough. In which case I just have law of inertia. My velocity is not going to change. Okay? Its gradient is going to be 0. So in that sense, I kind of have to know what my situation is before I apply the equation. And a lot of nonlinear phenomena does behave that way. So we do have to kind of take a look at what is actually happening, or test what is actually happening in front of my eyes, and then apply equations. So in that case, we actually did solve for both of those cases. And we actually got that, hey, in case that I don't have shear stress that is large enough in my tube, nothing will happen, so there will be no velocity distribution. But in case that it's somewhere in the tube, we know that shear stress changes. And it goes from basically 0 in the middle of the tube to some maximum value on the solid boundary. Okay? So if somewhere in between at some radius, okay, I actually have shear stress that is large enough in absolute value. So here I'm looking at only half of the tube. Then in that portion, I'm essentially going to get my parabolic profile, and things will behave as if they were Newtonian fluid. And in the rest of it, I start having a solid plug, and I don't have a relationship between shear stress and a velocity. My shear stress is still a certain value. It's somewhere in between 0 and that yield value. Okay? But it does nothing to my velocity distribution. So basically the response changes because I have a different type of material. So here I basically just keep the velocity that I had at this point. If this velocity was 0, well, then everything is 0. If this is something positive, then that plug is moving at a constant sort of velocity throughout this region where my shear stress, throughout this region where my shear stress is not large enough. All right, so that is a Bingham plastic. Now, we could also have so-called shear thinning or shear thickening fluids. Basically, my viscosity coefficients appears to change with the amount of shear stress that I actually, or amount of shearing that I apply to this fluid. Okay? So essentially, it could get either smaller or higher. So it could either get like easier or harder to for these fluids to move. So in that case, I have a very common so-called power law, two-parameter power law model, okay? Which says some m is essentially what my mu was. Okay? Well, sort of. Actually, this entire term, m times dvx dy to the n to the minus 1, this is my apparent viscosity, which is why I don't want to use mu here, though sometimes mu is used. Yes.
When you point something on your screen, it doesn't appear in the same place on our screen.
All right. So there's a lag. Okay, it's a little slow. So this entire thing here, okay, is what my mu was. So my mu now is not just a coefficient. It is actually a functional relationship also between the gradients and or at least that's what it is effectively. Okay, I don't like defining viscosity that way. I would like it to be something independent from my gradient. But if I want to compare to my original form of Newton law, then basically this is what my effective viscosity is. Okay, so if I have n is equal to 1 here, then this term disappears. So I'm still basically falling down to Newtonian fluid. So this description does allow Newtonian fluid within. If n is less than 1, then I have so-called shear, thinning, or pseudoplastic. And blood is one example, and so is foam. And if I have n is larger than 1, then I have so-called shear, thickening, or dilatant fluid, and that was sometimes you go in between, or you could be combination of that Bingham fluid and power law, so cornstarch could be modeled either way, or sand suspension in water. Okay? So what makes it so? When I have Newtonian fluid, the base sort of fluid that I'm thinking about is water. The size of a molecule of water is way less than 10 to the minus 6, 1/1,000,000th part of a centimeter. So it's about way less than 100 angstroms. And origin of viscosity is basically exchange of momentum between these molecules. However, I might have a complex fluid that either has particles, solid particles within, that are now interacting with the molecules of the original fluid. Or I could have a complex fluid that has polymers within. And these polymer chains, they can be very long. Kind of when I think about polymer chains, I kind of think about having a clump of long hair in the water. Okay? And these molecules, the way now they interact and move around and exchange momentum becomes really complex. And it really, I become dependent on what is the form of that hair in the water. Okay, what are the forms of that clump in water? So I know from experience. I know from experience because I have long hair. So if your hair goes down the drain, if it goes elongated and all of it is kind of parallel to each other, it's just going to go into the drain and go up. However, if it mixes up with soap in some weird way, it starts clumping up and it becomes a plug, okay, in your drain. Because all of these sort of polymers or my hair have mixed up in this clump that is not moving in the same way because of the structure of that clump. So the fluid starts having structure underneath. And basically, whether these clumps are elongated or they're actually plugging can change the response in terms of viscosity. And now, again, these long polymer molecules, they're on the order of 10 to the minus 2 centimeters. That's 4 orders of magnitude larger in one direction, not in all directions. Okay. So that can basically, they can tangle or untangle at higher shear stress rates. So that's one type of behavior. So when I actually put that down and plot it, basically using some of these example values for M and N, my black line is still my Newtonian fluid. I know that Bingham plastic is just simply shifted by this tau 0 here. Okay. Now in terms of shear thickening fluid, I can see that for lower shear, okay, I'm going to have one coefficient here, which is the tangent or slope of this line. Right? And for higher shear, I'm going to have larger slope. Right? So that's what I mean by thickened. Okay, my viscosity increased, effective viscosity increased. And here for shear thinning, I kind of have the other way, other way around. For lower shear, I have a higher slope. And when I look at the slope, again, this is my slope. And it's a functional relation. Still lagging. This is my slope. This entire thing, right? And it's a function of the shear that I'm plotting against, right? So for shear thinning, here, the slope is more steep, okay? And here, the slope is less steep, so I'm thinning out. It's easier to move. My effective viscosity decreases, okay? Because it's effectively a function of shear rate. It can actually get worse. Yes?
Shouldn't the x's on that graph be dvx dy?
What did I plot? Yes, it should. And I have this probably for the past 3 years or so.
Yeah, the XC switch,
Yeah.
the Y, the X, right?
The tau yx,
Yes.
dvx, dy. Yeah. Yeah, it should. That was a test. Alright, so I'll have to actually remember to change it so that I don't have it for next year again, the same thing. Alright, so it can actually get more complex. As I change the shear rate, I could actually have my material degrade. So it's not only that shearing affects it, right? But there could be, even as I'm keeping the constant shear, like I get certain shear rate, okay? And I'm keeping it up. As I'm keeping it up, I like to imagine I'm beating up my, my structure, and the structure simply degrades. There's fatigue in the material, okay? And can change the material properties itself. Okay? So yes, I would like to, let's, again, if I'm really like shearing a polymeric fluid, it has polymers inside, at some point, not only that those polymers detangle, but they also, even at a constant rate, where it should kind of keep up the same effective viscosity, it doesn't, because my polymer maybe they start breaking down in two, or something else happens to the structure as well. So even though I'm keeping the same shear rate, basically my material is changing, and that then changes the effective viscosity, and we refer to that as time dependent. So I might be keeping the same shear rate, but with time, my fluid will change. So there's two of them, thixotropic and rheopectic. If you wake me up in the middle of the night, I'm not gonna remember which one is which one, okay? But I do remind myself. Now, that said, for the most part, we're still in terms of modeling, okay? I might know that the fluid is changing in time. Okay? I don't necessarily go to complex functional relationships to describe this. I still work with this effective viscosity. So typically from measurements that I have in the lab, I will figure out what my effective viscosity is for all situations, and I'm going to use that. So if I'm doing simulation or anything of that sort, I'm going to think about the fluid as temporarily Newtonian with an effective viscosity. Okay? And then I'm going to march forward in time, and then I'm going to change that viscosity and again pretend. So it's quasi-static or quasi-Newtonian situation where at different stages, okay, I'm going to adjust my effective viscosity, but I'm going to basically model the fluid as if it had a constant viscosity. I'm just going to change that constant as I march through. So that is most common. Now, just to tell you where this shear rate terminology came from, and how do I now just quickly generalize this to a more three-dimensional situation and not just relationship between the two. Now, if I had my tau tensor, Okay, so this denotes, again, I'm going to have a lag here. All right. My tensor here, okay, I know it depends on my Jacobian of velocity and its transpose. So this is for my incompressible Newtonian fluid. I can still compute that for regardless of whether it's compressible or incompressible. So what we typically refer to this entire tensor, okay, as so-called rate of strain tensor. Now what I refer to as the magnitude of this tensor is, and this is the shear rate that I'm talking about. In the simple case that I had, it was either dV/dr, absolute value, or absolute value of dVx dy. Okay? So when you compute that for the very simple situation that we had of having only non-zero Vx velocity and dependent only on y, then you're going to get absolute value of this. But if I didn't have that simple situation, I had a more complex situation, what I would compute is this is a product. Basically, I go and take matching positions in my tensor, and I multiply them up and sum it all up, okay, for two tensors. And here I'm taking it tensor with itself. So it's going to be dvx dy times dvx dy plus dvx dz plus dvx dz, and so forth. Like, I'm just going to add for all of the elements that I have in there. Okay? So essentially, when I do that computation for something that has only Vx, that is not zero, then I'm going to get this absolute value. Okay? We are rarely going to go into this at all in terms of computation. I just want you to know what do you need to do if you have a more general situation. Okay? For any kind of non-Newtonian fluid, if we do have situation, it's going to be this simple one where I have only one non-zero velocity, so your shear rate is either defined as this or that, depending on the coordinate system. Okay? All right, and this is my, in power law, this is my effective viscosity. That's what replaces viscosity mu. Okay? All right, if you need more details, this is chapter 8 in the essay.
What it says, and all
other velocity components are zero.
Thank you.
By December, you will be a pro in reading mine. Too late. The semester is gone. All right. Oh, never mind. Let me just now. And these slides are posted. So again, this effective viscosity of a non-Newtonian fluid is a hypothetical Newtonian fluid that would effectively give the same shear stress, right? So basically, I compare things to Newton's law, and I compute what that effective viscosity would be. Okay? And I could do this for any kind of complex fluid. We will typically just talk about effective viscosity. Now, what happens if I actually have compressible situation? We're going to start working on that, and then we're going to finish next time. So what if I actually have a compressible fluid? Okay? So let's say that I have my familiar horizontal tube. Okay? And one thing that I know already about that tube is I know a general form of z momentum balance. We have already done that, so we're not going to redo it. And basically this form, this general form, so for horizontal fluid, my body force is not relevant, so I'll have a 0 here. And my z momentum equation is the familiar one right here. Now I actually have to figure out, well, what to do instead of phi for something that is compressible. Okay? It's still Newtonian. Okay? So if I remind myself, my viscous stress is described with this portion. It's just that there is a portion here that is not going to disappear. So I will have a non-zero divergence for compressible fluid. And then I have this term 2/3 mu minus kappa, kappa being dilatational viscosity. For the effective case that we actually will solve for, we're going to assume ideal fluid, and for ideal fluids, kappa is 0, but I still have this 2/3 mu here. Okay. So it will actually enter our equations. So key differences is that there's this divergence term that it doesn't disappear. Okay. And that actually also affects, so if I can compress and decompress locally, my density will not be constant. Okay. So my density can respond to different pressure and velocity. Normally, if I assume incompressible fluid that doesn't locally compress and decompress, then my pressure and velocity kind of respond to each other using these nonlinear equations. And density remains constant. And now I actually have density enters the mix. So all three respond to each other. And there's this pairwise relationships between them, if you will, that I have to kind of untangle. And I also have to have then help of my equation of state to define some of these relationships. Okay, and how do pressure, density, and velocity change as things change. Okay? So I might have velocity that will respond both to local pressure and density changes. I know that pressure and density are typically related through equation of state, or we model them. So there's this complex relationships that go all possible ways in there. Okay? So the differential equations that we worked with is nonlinear. So now it becomes kind of harder to untangle what's going on. Essentially have sort of one more degree of freedom, one more dimension to an extent. Okay? So if I apply a force to a compressible fluid by imposing a pressure gradient, for instance, in a tube, okay, then I might have actually this local change of density. So before this, in incompressible situation, everything was kind of, all of this application of force was transferred to the momentum change. And now I have some of it actually go locally to the density change. Okay? And things start interacting. So immediately next to this force application, my fluid will, once I apply it, my fluid will get a little denser. Okay? If fluid locally gets denser, that means that next to it I have fluid locally become rarer. Okay? Because I have constant amount of fluid to go around. So basically then I start suddenly having this denser, less dense, denser, less dense, denser, less dense. I start having this wave within my fluid. And so basically my pressure, because of that pressure is related to the density, becomes a nonlinear wave as well in response to those density changes. So I can't assume, oh, I have this nice little gradient of pressure going from one value to the other, whatever it is that I imposed, from one side of the tube to the other. So it becomes this more complex. And in response then, velocity, since it can, is going to start changing in radial direction because that's the direction it can go to. So I might have some local changes both in radial direction and z as I go along. So my velocity will locally respond to these pressure/density changes as well in a complex way. Hard to think about. Let's actually solve. So I'm going to hope that the pen has worked a moment ago. Let's hope that it does right now. And if not, I came up with a solution. You know how screens don't react when you have a glove? So I went by a lab. I got my. So if this pen is not behaving, I have a solution for it. All right. Though I rebooted things and it was working a moment ago, so we'll see. All right, so our example, yeah, so far so good. I was looking forward to trying out my glove. So compressible Newtonian gas or ideal fluid in horizontal tube. So my tube looks like I would expect it to. It's still a tube of radius r and length L. Have z direction. I apply a pressure difference. So my pressure, I will assume that pressure is a function of z only. Partly because I'm applying a single pressure value on one side of the tube and a single pressure value on the other side of the tube. I possibly have P as a function of both R and Z throughout the tube because of these responses. But because nothing is coming from the R side, I'm going to even think about this P is basically integrated along these Z slices. So I'm going to just look for that average value. Okay. But I'm just assuming that these pressure differences along those slices are not large enough. And for good enough push or pressure difference, they're not going to be large enough. So this is for simplicity. Assume for simplicity. I can't assume that both pressure and velocity do the same, though. So my velocity will respond to changes and change possibly in radial direction as well. So my velocity, Vz, is Vz of Rz. And it's non-zero. I will still assume that my VR, nothing is effectively flowing in R direction because I don't have a pressure gradient moving it in that direction. And my V theta, R0. So it's not much more complexity, but suddenly we're going to be solving for 4 pages instead of 2. Okay? So only really this addition here of Vz is Vz of Rz. So my Z momentum remains the same. So Z momentum balance is minus phi zz partial z minus 1 over r phi rz r. So what is my phi zz? I have pressure. What else? Tau zz. What else? Okay, so what is tau zz?
Minus mu. 2 times the reality of Vc with respect to C.
Mm-hmm.
And then you have the divergence term.
Times? What is divergence?
The reality of Vc with respect to C.
So technically I need to find divergence in cylindrical coordinates. Can somebody look it up? So somewhere in the, nobody wants to look it up. Great. Okay, so just remember don't assume that this is something the same as dvx dx plus dvy dy plus dvz dz. It's not that simple for cylindrical terms. However, in this case, vz is the only non-zero one, so it will simplify simply to dvz dz. Okay? But it's not dvr dr plus dv theta d theta plus dvz dz. That's not what it is. Okay? There's somewhere in there 1 over r something, okay? So just remember, in cylindrical coordinates, it's never as simple as in... So look it up, okay? 1 over r, where? Somebody is actually looking it up right now? Yes, so there's 1 over r term in there, then what? Mm-hmm. So, yeah, so dvr dr. Luckily, we don't have vr, so that term is gone. Then?
And beta 0, 2, so we only have this partial vz over partial z.
Right. So what I'm saying is that actually, nominally, it looks the same as if I had the cylindrical, the Cartesian coordinate system here, but I don't. It's the same only because most of the terms are 0. Okay. And plus rho vz squared. Okay. Now my kappa is for, it's 0 for ideal fluid. Right. So we're going to have vzz as pressure. I have minus 2 plus 2/3, so minus 6 over 3 plus 2/3 is 4 over 3, mu dvz dz plus rho vz. And my phi rz is, do I have pressure? No. Tau rz. And that is minus mu. Again, I have the term, again, actually look it up in cylindrical coordinates, what tau rz is. I have dvz dr plus vr dz, but vr is still 0, so it still simplifies to dvz dr, which is what we expect. And then another thing that we're gonna assume in terms of, so let's just put it in to see what it looks like, and then we're gonna throw in other assumptions. So I have minus d dz of pressure dvz dz plus rho vz squared minus 1 over r ddr of r times minus mu dvz dr. So that is my equation. What saved us last time around is that I did not have a dependence on z. Okay? So these two terms, basically dvz, this one was 0, and then because essentially divergence was 0, and this one here, my vz did not depend on z, so the moment I did dvz dz of this term, here, do you see this one? Okay. That one disappeared last time around because my vz was only a function of r, and now it doesn't. Okay. So I have a coupling here of multiple partial derivatives. I have a partial derivative of z with respect to z, not only of vz, but also of vz squared, though I can do a chain rule on that. And I have a partial derivative with respect to r. And I have a derivative in pressure. And they're not even like, I might have second order terms, not only first derivative, but also second order derivatives. So it's altogether a yummy equation to solve. Okay? And it's all of that thanks to dependence. It's like, define your own yummy, Dr. Pradanovic. You might think it's yummy. All right, so basically, and all of that is brought by Vz being a function of both z and r, which is, please, if you can assume that your velocity is only a function of one variable, please do. We're going to continue this on Friday.